我们今天来讲最后的，我们之前说过，我们会用几个 example， 今天是最后一个 example 来，去解释基本的这个数学上用的方法。今天我们想用这个 example 做一个，我不知道我的翻译对不对，我还是用英文好了，是 monotone dynamical system 它的一个引入 ，OK。So let's see, how many of you have seen this before or saw this somewhere? So this basically is, remember, back to early of 1900. So Ronald Ross, who is a medical doctor and formulate a differential equation model to study malaria. And he indeed received the Nobel Prize. Yeah, because of this. And anyhow, later, McDonald and further develop this model. So now I'm going to put it together to show you what's this. And this is for malaria. So there are two populations involved in malaria. One is the human population. So let's put this is the host. And the other one is mosquito. Human mosquito is vector. So basically the idea is, and so if a person bite by infected mosquito, and the person potentially can get malaria. And the other way around. If a person got infected, but bitten by what? By a mosquito. Mosquito may be susceptible. So then the mosquito, because bitten the bite, let's say, bites the infected person, also can get infected. So that's the big picture. Let's see. So now we're assuming in both the host human population and mosquito population, they follow the SIS. We talked about this in the very beginning, the fundamental classical epidemic structure, SIS. What that means? That means in this case, actually, we neglect the immunity. So there's no R. See this? So now let's call this is host. So this is for the vector, the mosquito. And then we need a lot of more space. So we can see this is the birth rate, the simple demography. We saw this before. This is death rate. And then the infected human host can become infected. Let's see what's our notation here. So here is H. And also the host can become recover. And then the other one. So this is so it's a B. And then of course, mosquito can give birth. And now, So here, what's H? H is the total host population size, and V is total mosquito population size. And what's the big assumption we did is we're assuming host, humans, and mosquitoes. Actually here, the mosquito really talk about female adult mosquito. The vectors follow SIS epidemic. And now let's see this, what's the, maybe I should give a table. Yeah.
In second, SP by X or V.
V. You talk about this?
Yeah.
Yeah. We'll see this in a second, okay? I'll show you step by step, but give me a second. Let's define everything we have, okay? Bear with me. 他刚才问这一项是危险，we'll talk about term by term. Just give me a second, okay? So here, what's the variables we have? We have this is the number susceptible human on the host, susceptible human host. And so let's talk about infected. And here, this is susceptible female, basically adult female mosquitoes. So the vectors. And here's everything, but it's infected. And now, what parameters we have? We have lots of parameters. A, B1, two, what else? H, gamma H, gamma V. So A is the biting rate. What this means? Think about this basically. So if you have one mosquito, this and that's basically how many bites they're going to be made. Or roughly you can think about this, how many humans they're going to be bitten by one vector. Does that make sense? So just like each of us, we typically have 3 meals a day. That should be good enough. If you get enough food for each meal, 3 meals a day should work, right? But then this is captured, say, per unit time, say per day, how many bites or how many vectors they bite, okay? And then B1 is the probability. Think about, even your bite, doesn't mean your bite will transmit the disease to what? To the host. So B1 is the probability that the human infection or the host infection actually take place, let's use a simple word, occurs in an infectious vector. Then B2 is a probability, and when what? When a susceptible mosquito bites the human host. So sorry, but the other way around. When an infected host is bitten by susceptible mosquito. So let's talk about the vector infection. Then mu H is the death rate, host death rate of human. And here mu V is the death rate. As you can tell from the subscript, H is the host, humans, V is the vector for mosquitoes. So this is for vectors. And gamma is in recovery. Post recovery. And this is vector recovery. So we got all the notation cleaned up. Now I'm going to add this one. So we should use this. So this one, not this part. If we don't want cross, maybe we do this. So vector can infect host. And also, and host can, sorry, this way. Host can infect what? To the vector. Because when the vector, if they're susceptible, even they're healthy, 易感的, but when they bite 感染的人, infected human host, they can get infected as well. Yeah, so, but this is not the direct things. They have what? Basically cross transmission. Now, let's see this. We have two, looks like non-typical. Before we talk about the disease incidence rate, looks so simple, right? So now let's see this. Now let's first talk about so this is transmission in host, the human. Okay. So as we see, let's see this term by term. Let's see if we understand this. First of all, we start with one infected mosquito, but one mosquito. And then this is say on average, how many bites or how many human hosts going to be eaten by the mosquito per unit time. It's a rate per unit time. But even you bite the person, it's not necessarily means the person got infected or the disease can transmit it to the person. So this is the probability for this infection to be affected. Then among all the people, the human host, they bite, and this vector bite, and only what susceptible human host is what you want. So this is what the likelihood the host you bite is what? Susceptible. So overall, this gives us the effective bite in human host, and which we can see malaria actually transmit from vector to host. And then at last, we multiply what? Number of vectors you have. Of course, the more you have, and this transmission rate is going to be higher. Does that make sense? So you can think about this like what? Beta, right? Beta. We saw beta so many times, right? So it has two parts. First, you got to bite the host, right? A telling you how many hosts you're going to bite per unit time. Let's say per day, whatever. Then even you bite doesn't mean the host will be infected, meaning the bite is not necessary to be effective. So you are going to be able to transmit the disease to the host, and B or B1 is the corresponding transmission probability. And also among all the hosts, when the mosquito bite infected human host, it's not in your concern. That's not something you care about. You only care about if the host is what? Susceptible. Then SH over capital H is a fraction of the probability or how likely and the person you bite is susceptible. Does that make sense? And then if we start with one vector, IV is 1. But now I sub V telling us how many vectors we have. So this is the total what? Transmission rate in host. Let's see. Do we have any questions? Is this clear? Are we happy with this? Good. Yeah, 老师你讲. So let's see. Then we also have what? The transmission in mosquitoes. So now I'm going to use another notation, and let's see where is a good place to put. I'm going to add another notation. This is biting frequency. It's basically saying if you are a human host, and on average, how many bites or how many mosquito will bite you per unit time. So that's a tilde. They're different. One is talk about like how many meals a vector or mosquito can have, right? This is talk about if you are a human host and how often you're going to be bite per unit time. Like 一天你大概最多被叮几次，这个意思。对。And then B2 is even if you bite, similar thing, and this bite has to be effective to be able to transmit it. That's the likelihood, transmission probability. And also, you start with what? You start with an infected human, right? And then a tilde telling us how many mosquitoes bite you. And B2 telling you even if you bite, that means if B2 is 1, sorry. B2 is the number between 0 and 1. It's not necessarily means you got infected. Mosquito got infected. So this is the probability mosquito got infected. Also, among all the mosquito, you only care about whether or not the mosquito is what? Yeah, susceptible. Uh-oh, I copied this wrong. Sorry, this is 18, this is H. Yeah, let's do this step by step. This is the V. Does this make sense? Does this make sense? No, let's focus on this. Does this make sense? They're different. Give me a second. We will be there.
Yeah.
They are, this idea is identical like this. All I did is swap who is vector, who is the host. Identical, right? But notice what? The total number of bites. If I start with vector, that's how many hosts they can bite, right? How many bites they're going to do. And it's same as I start with the host, and this is how often or how many bites a host can receive. This is the total number of bites per unit time. They should be the same, total number of bites. This is how many vector. This is how many bites a vector can make, right? Say per day. And this is the host. This is how frequent, say 1 day, the host will be bitten by mosquito, right? So this is total bite. They're the same. Then this is saying what? A tilde is basically V over H, right? Let me know if I copy anything wrong. See, and he already catch I copied that wrong, right? So we got this. Does that make sense? Now I'm going to use this one and substitute right here. Then let's see what we got. So we have A, V over H, V2, SV over V, IH. I just copy everything we got. Then clearly what? Clearly, you cancel this, right? Then what's left? That's exactly what we put over there, right? This is exactly So this is exactly, so let's rewrite this. This is exactly to what we have over there. Sorry, IH. So this is the two ambiguous pieces instance. Is this clear up? So far so good? 清楚吗？可以吗？就是这两个看起来比较复杂的，其他的 all the other I think directional arrows you guys can see it clearly, right? Either simple burst and dice or recovery, right? That kind of thing. So if this is clear, unfortunately, I think I would like to save this. I'm going to clean this piece. Would that be okay? Are you guys done with this? For the student who came in late, is this okay if I clean this part? Thank you. 现在 this is all in your mind. I have to erase it, unfortunately. Sorry. So in Taiwan, maybe one of the famous, I forgot to say, this is called vector-borne disease, right? So one of popular, I would say, vector-borne disease probably is dengue. So now let's see this. So put together, now we can write down finally the model. The model is called N5. We have what? Again, the prime is DDT, okay? So mu H minus I may know if I copy anything wrong. So what I'm trying to do is following that. Oh, this is wrong, right? This should be what? The dash free. This is dash of the vector. Is this the same as that? You guys can double check. I'm too close to the model. 是这样吗？好。现在第一件事情 we're going to do, I'm going to use the fraction variable or the proportion variable. Because what? Because what? So let's focus on the first two equations. When you add it up, you get what? You get h prime. That's equal to what? Can you guys see? What do we got on the right hand side? We got this, right? What else? Many terms cancel. What do we got? What's left? This term cancel, right? What else? This term cancel. So what's left? Those two terms. There's this for a second. You notice anything? What's the last two terms? So you have oh, what's this? The host population size H. So this is, yeah. It's what? Yes, it's 0. What that means? So the total population size for the host is independent of time. In other words, constant, right? It's constant. So that's why you see why when we wrote it down, we keep writing this, right? And likewise, you can check the vector population is constant. The same as the initial size, we denote it as H. Okay? So now, because the total population size for the two involved populations, one is a host, human, and the other one is a mosquito, they are maintained at a constant size. So we're going to use fractional variable. What's that? So it's a proportion. So when we rewrite this, we have, sorry, those looks almost identical. It's pretty confusing, huh? The small one means the fraction. Yeah. So what we have. So I introduce another variable that's called M. M is what? Vector to host ratio. Vector to host ratio. Because V is constant, H is the constant. So what we have, this is a little sh. This is the same thing, just rescale everything by the total population size. You can see immediately when you divide everything by H here, everything H here, you will get the first two and the last two equation divide everything by V. The 文字的总数 divided by V, you will see this. But now, remember this. This means a lot of things. This means when the population is close for both the humans and the mosquitoes, what we can do? We like that. We have certain type of what? Conservation relations. So with that, what we can do? Conservation means what? If I know S say host, number of susceptible hosts, because total population size for the host is fixed. It's constant. So you can immediately tell how many infected humans, right? So what that means? That means we can do dimension reduction, like 2-dimensional reductions, right? Okay, let's do that. You with me, right?
Yeah.
是哪写错了？
recover 是这样，
recover。
下面那个第一条，
这个，哦，这个，谢谢 ，Thank you. That's really nice. See, I'm trying to see if you guys paying attention. Good job. Let's do this. And because of this is what? Because we normalize this is the fraction. Total fraction is 100%. Is 1, right? So I'm going to use, instead of writing SHIH, so many like subscript, and also it's hard to distinguish. So I'm use my favorite variable. I will use X for IH. And so Y for IV. This is the infected host, fraction of infected host. This is the fraction of infected vector. So now SH will be 1 minus X, SV will be 1 minus Y, right? I just replace the name. It's so hard to tell which one is which on board, actually. You with me, right? So now, with the conservation, we have the following. So I use another notation.有点像什么？那个种群 computation 的 model。这里的 gamma one 是什么？是 mu h plus gamma h。gamma two 是 mu b plus gamma b。Basically, I concave those two together. So far, so good. We like this. We already talked about this last class. This is say, and we can use the technique what? This is a 2-dimensional model. There are a whole lot you can try, right? 2D model. So first of all, again, the S and the Y, they're fraction of infected whole humans, or this is a fraction of infected mosquitoes, right? So clearly, this is a real biological problem. Of course, everything has to be non-negative. What else? This is one bond. Yeah. Bounded about by, because it's a fraction. So that's another benefit of normalization, right? Okay, all right. So this is clear. Now you can easily check, super easy. I'll give a name for this region. It's positively invariant. We need this. You are, once you start in the biological physical region, you stay there. So positive just means you move your time clock forward, right? You start there, you run your system, you stay there. So positive invariant. This is important. This basically means the problem is well posed. You need to check, like every problem you like a model you formulate. This has to be true first, meaning something has to make sense in whatever the context. Doesn't matter you work on infectious disease, you work on like biology or physics, chemistry, same thing. You have to check that first. Then just in case if the model touch the boundary can go below, then you're in trouble. in some sense, it's not a good model, a reasonable model, well-posed model. Okay, all right. So now, oh, this is an interesting thing. So let me write it. We need one more word. So later, probably you will see this a lot, basic reproduction number. And if you use, we talk about this is what compartmental ODE model. How we're going to compute R0? How we're,
Next generation.
very good. Excellent. Use the next generation matrix method. So for instance, if this is the partial differential equation, and in that case, you're going to use next generation non-matrix operator method. And then to compute, to derive R0. Then we see, I thought that I have to erase this. Now we see R0. Do you know? Do you know what's the R0 in this case?
For this model,
Yeah.
oh, I cannot guess. I have to complete. Oh, yeah.
Oh, so let's see this term by term.
There is one query.
Yeah.
Your definition of R0 is this is definite, or you can get it from the active matrix.
You can do it many different ways. I'm saying this is a standard recipe. We all know, right? Using this, you can calculate. Then you see this weird stuff. Okay? I'm going to show you why this is the case. I'm not going to do the calculation. I think I'm going to leave it for exercise. Is the standard calculation. You figure out what's the next generation matrix K, you calculate the spectral radius. It's just a little bit long. You probably need one page or something. You need a couple more minutes. But now the point is they get this strange expression and something with square root looks so unusual because the typical things we see before is like fractional form, right? Nothing like square root. Let's check this out. That's what we're trying to do now. You with me, right? So let's see this. What's this? So the top is what? Number of byte one vector can make per unit time, right? And even you byte, it doesn't mean you transmit it times the probability is transmitted, right? So that's basically every number effective what? This is every number effective human host got infected per unit time. Then how much time the vector can live in the infectious class is 1 over gamma 1. So times the total time duration. So this give us what? This give us the number of the host of humans infected by, this case is 1 mosquito per unit time. Not per unit time, it's not per unit time because you times everything by 1 over gamma 1, this total duration. That's how much time a mosquito can stay in the infected category. You with me, right? This is similar to like the beta over gamma stuff we saw before, right? Beta over gamma, huh? Okay, similarly, let's see what this. AM, that's what I say, unfortunately, I erased that. AM is A tilde, is what? Biting frequency. Is say if you're a host, that's how many bytes you receive. Or in other words, how many vector bite you, right? And times, even you bite, doesn't mean you transmit the disease. To make this to be effective, you have to transmit the disease. B2 is the transmission probability. So on the top is what? On average, how many vectors will bite one host per unit time? But it depends on how much time people, the host can stay in the infected category. How much time is reciprocal of the recovery rate is 1 over gamma 2. That's total time, right? So this is what? The number of vectors, mosquitoes infected by one human host, from host to vector. So far, so okay? Is those two small part okay? 有问题吗？有问题一定要讲。我们就是 make sure every step， 你看我们都是从 very beginning 来 talk about 这个 ，make sure we are all on the same page。有没有问题？有没有 comments、questions、concerns？ 请讲。
我刚才的 M
A. Oh, M is vector to host ratio. So AM is A is the biting rate. A tilde is the biting frequency. 你们记不记得我们推导那个 A 和 A tilde 之间关系的时候用到了这个，就是这个。
So this
Eh?
in comes in the second equation or first?
No equation becomes conservation law, and because the total population for host human is constant. And also similar thing happened to mosquito population. Vector is considered constant.
Equation is
So vector to host ratio is a constant, so that's M.
equation is the first equation.
Yeah,
There is no B.
no what?
B in your first equation.
There is a V. V is incorporated here. V is incorporated here. This is a vector to host ratio. We did this just step by step. If you follow what we just did, they are the same. All this X, Y stuff, because if we keep writing IHIV, it looks so confusing, right? So we use two of our favorite variable, let's say X, Y, to rewrite. This is the same thing. Where that M coming from? It's coming from right here, this term. This AB1M, I just erased.
There is
percentage in your evaluation. Just focus.
oh, it's okay. It's
你说
Point products. 那个是减 Y 啊，还有一个
哦，对，这一定是减 Y，没错。对，你看这个就是有时候你离现场太近的时候会有这个问题。对，谢谢 ，very good，thank you。所以老师一定要来，开始这个一定要，因为学生会 confuse，非常好，谢谢。对，Are you okay?
Yeah.
This you can easily this math everything looks messy, but if you follow that, it's super straightforward. Nothing fancy, nothing tricky. But the point is, we want to get this. This is the first time probably in this class we see the basic reproduction number square root something. We're trying to understand what's going on, right? Okay. All right. Now let's see this. Now we see the infection to be effective because what? Let's see. What's R0 telling us? Can anyone tell us? Expert, what's R0 telling us? What's R0 is trying to tell us?
Secondary cases.
Say that loudly. Secondary what? Now you have two population involved in the business. Host, human host, 人类 vectors, mosquito, 蚊子 right? 你关心的是您比较关心的是谁 ？Human， 所以你可以想什么？因为是 primary case, start with primary case. You want to know how many what? Start with one person got infected. 如果 no one got infected, you don't care, 对不对 ？Start with one person got infected. 然后你想知道什么？R0想告诉你什么？你想知道什么？你说。那得说没关系，没关系。
有多少一个这一个人有感染症？
对 ，excellent. So how many newly infected? I'm going to put newly infected. You will see why. Because if this person got infected, cannot immediately infect another person. You have to go through the vector, mosquito, right? So I would say the average number of newly infected what? Human. How should I say that? Say produced or induced by one infected human host. Of course, in the host virgin population, there's not only one. Over the infectious period. 现在问题来了 ，You start with one person, you cannot immediately affect or transmit this to another person. You have to go through the vector, the intermediate step, right? So what's going on is this. You have to go through 2 generations of the infection. One is from human to vector. This is one transmission rod. Then from vector to human. So this is from H to V. This is from V to H. 2 steps. This is step 1. This is step 2. So meaning I cannot directly think about secondary infection. This is a 2-generation thing. 因为从感染的人开始，你现在感染的是蚊子，这是第一步。第二步再从蚊子开始再感染人，这是第二步。你才能从人到人，从 human 到 human. It's not immediate. 2 steps, right? 那 the first step is what? The first step is this, right? From host to vector, right? The second step is doing what? From vector to host. 因为是2个 step， 可是 next generation telling us 是什么？是 secondary infection， 是 per generation, average number of secondary infection per generation. So what they are going to do, you have 2 steps, and typically the 2 numbers not supposed to be the same, right? So what are you going to do? If they're identical, that's easy. Square root is the same thing, right? So we take the geometric mean of the 2 generations, take square root. This is called geometric mean, right? Not algebraic mean, the geometric mean. Algebraic mean is a plus b over 2. Geometric mean is square root a times b, right? So that's why you see this. 这清楚吗？可以吗？同学，你有问题吗？等你 if you use 这个 next generation matrix method, you will see the stuff very long and super complicated. And basically now we're trying to bring it down to see why this is the case. 我没有 enough space，我没有写，因为这个 R0是 per generation thing，per generation reproduction。你既然你要 take 两个 round，我 take 它的，我是不知道叫几何平均值 geometric mean，所以就会有这个，就是这个意思。因为说白了就是两个 step，if you go through two generation， 是不是 effectively 就是 think the stuff without square root， 对不对？这就是 effectively thinks how many things going to be happening， 对不对？我说如果你 go through 两个 step。R0 squared 是不是 exactly equal to the product of those two complicated terms， 对吧？那现在既然你 talk about per generation thing， 所以我们 take the geometric mean， 就这个意思。这样可以吗 ？So far so good. You guys now look very happy. So I'm trying to check in. Are we all good? Okay.
Sorry, little is
Hey.
the location of M.
Yeah, I'm
Hmm.
saying the same thing. M should be in second equation.
Yeah, and AP1N or AP2N.
To do this, we need to go back to the very beginning.
M is vector to like human. So in second equation, there is vector to human population.
The first one is infected human, right?
Yeah.
This is a vector to human population. So let's see this, the very beginning. Sorry, I'm not going to write in all the stuff, but let's see this. AB1 SH HIV minus mu H SH plus gamma H IH. This is right?
Yeah.
这个就是这个 diagram 对，然后 we're going to divide everything by H. So what we get the fraction. So this is a mu H. So this is AB1 SH HIV H. So this is the mu H SH over H gamma H over IHH, right?
Yeah.
Is this okay? So 我现在把它换成，哎，这个 it's so hard to tell which one is which. 我把它换成这个。所以这个应该就是，我不把它写出来，因为写成小的。Can you guys see the small version? I'm trying to convert it to the fractional, but I don't know how small I can write. This one is little sh. This one is we need IV over V, V over H. That's exactly M. Right? This is a little sh. This is the gamma H, IH, right? Is this exactly, this one exactly is what? IV, right?
Sorry, 我的问题是说那个 RVIH 里面 RV
Which one?
那个根号里面的两个，然后里面有 M 的位置。我只是从右边那一个系统参数。
Are you talking about this?
Yes.
Oh, you're not talking about this.
Sorry.
OK， 没关系，这个要把它讲清楚是很重要，因为我们第一次是讲这样的东西。向老师，您讲。
那个参数是 AP1N。
你说的是这吗？
在系统里面是 AP1N。
对。
所以这边 R 为什么 AP1 跟 M 是分开？
不是，我这个算的不是用每个 term 这样算的， 我这个算出来的时候，不是用每个 term 这样算，你说的是，你看的是 AB1M 除以 gamma 1，对不对？AB2 除以 gamma 2，是不是从这里看的？你是这意思吗？
对，我只是不能够连解为什么 M 可以跑到那边去，还是说这个？
我是从 biological meaning 来看的，我这么画是这样子，我们当时解释了，来看这个 step by step，不着急。这个 A 是 biting rate， 是说一个 mosquito on average how many bite they can make。但是因为有 bite doesn't mean you transmit disease, so you got to time plus transmission probability. So this is effective bite per mosquito. 然后这个是说，即便你这是 per unit time， 对吧 ？Everything is per unit time. 那 how much time the mosquito which vector spend in its infectious class is the reciprocal gamma. So one over gamma 1. That's it.
So 就是在算线性系之后去做那些 value 的时候，
对，
它是乘着一起 A B1 M， 它只是说现在想要把它做解释，所以。
对啊，这就是我告诉你，就是说我说，因为这个 expression 看起来 so complex 嘛，而且 we have never seen something called square root. We're trying to break this down to see if we can understand this.
Just want to connect the system and the biological.
No.
meaning.
Not immediately. I think what you talk about is suppose this is 1, right? X is 0, this is 1. But you cannot see like this because at disease free Y is 0, right?
Okay, thank you.
没事。刚才那个 breakdown 清楚吧，对吧？我们是做的 term by term 的，清楚吗？就是不要 confuse，就是说怎么我们会看到一个 something looks like this， 很多的情形，当你 go through intermediate steps 时，可能你会 most likely 去see something like this。OK， all right。非常的好。If you have any questions, stop anytime. OK， 这个非常的好。I highly recommend it. 老师，你讲，你有问题说。
延续陈老师的话，
哎，
就是生物上怎么看那个 M 跑到那边去？当然计算上是计算成这样，就是有什么可以解释？
不是，我这个不是一个。One more time, I think you guys confused. This is the dimensionless version. This is not the original version. I think the problem is coming from here. I know why you guys confused. We're not. I'm doing this is simply for mathematical simplification, right? Otherwise, here will be h minus sh or some sorry, h minus ih. 我明白你为什么 confused 了。这个 x 和 y 不是 biological 的，是 mathematical 的，因为我们做了 simplification。当我们做 dimensionless analysis 的时候，那是它的 compensation。这是为什么你 confuse？ 如果你看 original model， 你还是会懂的，对吧？好，没事。所以现在我留一个，我觉得这是个很好的 exercise。And 如果你们忘记了怎么做 next general matrix， 记不记得上次我们 talk about 有一个 reference 是 written by Pauline van der Risch 和 James Waterman 的，有一个很 famous 的那个 paper， 你们去看那个 reference， 然后用它做一个 exercise， 这是我留的 exercise， 没有 nothing like homework， 你去 calculate 看一下这个 R0 长什么样，好吗？好现在我可能就把它。哇，这个怎么clean 呢 ？Do you guys mind if I clean the middle part? We're probably going to need the equation. Diagram stay there so you guys can have a better picture about the story, right? Is this okay? 不需要吧哈，我擦掉了啊，不好意思，刚刚讲过就擦掉了，可以吗？这个没有实质哈，这个中文是不是叫 delay， 叫实质是吧？这个没有 delay， 你 meeting 我就把这个黑板 clean。对，我知道老师为什么 confuse， 是因为我们做 dimensionless 的时候，它会有一些数学上的 number wise 的 compensation。
不好意思，我晚进来。
哦，不会，没有做这个，只是说我们都是玩数学的，对吧？我们看起来会比较 easy 嘛。 this model, I'm going to call this M5 prime, okay? Can you guys, at the most, how many equilibrium we can have? Just make a guess, two-dimensional model. There is one trivial thing you can see immediately. There is one trivial equilibrium, which is 对，说非常的好 ，you're so let's wait for a second to see if we can fix that. Okay. 有一个 trivial 的 equilibrium, can any of you guys see that? 还记得什么叫 equilibrium 吗？equilibrium 就是 set right hand side equal to 0， 就是 x 随着时间不动了，对吧 ？y 随着时间不动，有没有一个 trivial 的零点？哎，对 ，origin 对吧？说看起来有可能至少有几个 fixed point 或者是 equilibrium。OK 了吗？谢谢。OK 了？no， 还没。我们来想一下，在我们等的时候好吗 ？OK 了，好，谢谢 ，Thank you for checking。我们至少有一个 trivial 的零点，所以这个 system 事实上是 meet， 我不应该说是 two， 是 up to two at most two。一个是什么？一个是 infection free equilibrium， 这是什么？刚才已经讲了对吧？然后还有一个是叫 epsilon one。S star by star 长什么样的？这个就是 straightforward 的 algebra check 就行了，因为这两个 equation 都不难。是这样子的。我看着这个 expression 就有点晕。It's so complicated, huh? Looks like at least. Is there a better way we can say it? We already calculated R0, right? I'm going to use it to rewrite X star Y star. This would be way better. This should be a really good exercise for students. Even you just check why we're doing this. With this expression looks totally lost, right? So much, almost everything involved and so many parameters. But with this, what we can tell? When R0 is 1, X star, Y star merge together with what? This is free, right? 0, 0. But this expression, or if this is free, sorry, endemic or the second non-trivial equilibrium exists only if what? If this exists, everything has to be what? Endemic equilibrium means what? You sustain at a positive level, right? So everything has to be positive. So R0 has to be bigger than what? Yeah. So the pictures is clear. So we can apply the method we talked about. We use for what? For model 3. It's a simple MSR model with SIR model with simple percent depth. For that one, it's a 2D model, and we can do what? Basically, local analysis local stability analysis. 这个就是 linearization 嘛 ，global stability 我们用了 Lyapunov function 嘛，因为是二维的，我们 we also use Pankar-Bendix. The first one is the linearization. Second one is Lyapunov function plus Pankar-Bendix. So 同样的方法。 we have the following result. Again, there are two exercises I highly recommend. And if you're a student interested in this stuff, it should be a pretty good exercise. First is calculate R0 for this malaria, not the general malaria. This is just reduce. This is a Ross McDonald model, okay? Then check out the following threshold disease dynamic, okay? Two exercise. So the system of I has a unique equilibrium solution, which is disease-free. And this one is global asymptotic stable, the biological physical region. Second thing, if R0 is bigger than 1, we have the system has two equilibrium solutions. One is disease-free, the other one is endemic. And, oh, sorry, I have to erase this. And what? Furthermore, this is unstable. In addition, so this one is globally asymptotic stable in the interior of the biological physical region. It's not shocking. So for the malaria model, this is saying R0 also is what? A sharp disease threshold parameter. When you are below or equal to 1, disease die out. When you're above 1, disease persists. Where you go? You will eventually maintain at the endemic state. That's what this is saying. Okay, all right. But this is not the whole point because we did this before. So we're not going to do this again, but it should be a good exercise for students. But what I really want to do is this. There are a couple of things. First of all, the system M5, I just erased it, M5 here, right here, is what? It's a monotone. How many of you guys see monotone, some sort of things related to monotone dynamical system? Monotone dynamical system. How? Indeed, actually, is even strongly. I can't end that. Has strong monotonicity. What this means? Let's see. So let's consider general system. So we're not going to write this again. So we have a system like this. And so this is the R-dimensional system. So we don't really need to make alternate differential equation to well-defined there exists a unique solution. We don't really need FEC1. We only need Lipschitz condition. but this is stronger. Meaning we don't need such a strong condition. We only need if this condition. Anyway, so here's the setup. Now we say definition. So this system, what should I call system star? It is said to be monotonic or monotone. Another word you can say is order preserving. In what sense? So with respect to the partial order, induced by a cone in many cases, for example, in many cases, okay, K is simply the first quadrant. So you think about here's two-dimensional plane. In the first quadrant, this is local. So what this means? This means if initially you have such a comparison under the partial order, then it's going to be maintained all the time. Then you probably will think about, you probably will think about, I'm going to clean everything here, okay? So here, what this means? This means y minus x is in the cone, the positive cone, for instance. For instance, if the cone the first quadrant, what this means? Means y minus x in the first quadrant means component-wise you're non-negative. That's it. That's how you do comparison. So it's a vector, you compare them component-wise. This is a special example, a particular example only, okay? So of course, there are also something called strong monotonicity. Then we say system star is strongly monotone. What this means? We add this. It simply means this equality is replaced by inequality. We need to copy everything we have with respect to the partial order. If what? If initially you have such a relationship, you're going to maintain it all the time. So again, x less than y. 这什么意思？你想有两个数你比较大小 ，super easy right？有两个 vector 比较大小的时候，怎么比较大小 ？component wise 是吧？是吧？它这个 order preserving 就是这个意思，给你 maintain 一种秩序，是 whatever 的秩序。我们最常见的就是我们刚才说的 component wise 这种 comparison introduced by 这个 partial order， 是 y 减 x 要 in the， 不应该这样写。应该这样写， 这个明白吗？就是 y 减 x 要是 in the positive cone，但 y not equal to x。那换句话说，比如说看刚才这个example，如果这个cone是等于它的话，那这个就是说 y 减 x 是要什么？是 greater or equal to 0 for all the component, right? Because this time the cone is the first quadrant, but there exists at least one component, okay? Such that what? yi0 minus xi0 is strictly positive, meaning there exists at least one component you are strictly high. So that's what this means. That's what this is, okay? So this is strongly monotone. Let me clean this. Let's back to the Ross-McDonald model. 所以，有个更简单的方法，我在 go back 之前，我们应该 come back to this。等一下哦，有个简单的方法去 check，你怎么知道你的 system 是 monotone 或者 strongly monotone？我现在就假设 F in C1，因为 to make the system well defined, you don't need C1， 是 Leibniz 就好了，是 differentiable， 因为这时候你才能 check derivative。Then the general system star is still on the right hand side。这个地方把它改了。This is confusing. The general system star is said to be going to be monotonic. Oh, monotone. Not monotonic. This is monotone. If and only if what? This means if the necessary sufficient condition. You check. Look at the Jacobi. Look at the off-diagonal term. The off-diagonal term to be greater or equal to 0. 这事实上是另一个东西的 characterization. Something called the co-op.
Property.
Yes, exactly. That's how we can capture monotonic because 这个你至少得能 differentiable 你才能 check 它的 Jacobi. 然后 furthermore， 如果它的 Jacobi matrix， 你 check term point by point， 它是 irreducible。So this time, the system is going to be strongly monotone. So are we familiar? So if we have a matrix, so when we're going to say a matrix is irreducible. Anyone have some idea? What do you mean by a matrix? This is a functional matrix, but I'm saying if you fix X, so it's a constant matrix. What do you mean matrix is irreducible? How are we going to check? A cannot be decoupled. So a matrix is called, there are a couple ways you can do that. So constant matrix. Doesn't have to be square matrix. We all know what similar means, right? I wouldn't say upper triangular，应该是 block upper triangular。A block。换句话说，什么意思呢？就是说，你无论如何，你都找不到一个 matrix transformation. Under the new matrix transformation, you can rewrite it into a block upper triangular matrix. And 如果你看 graph 的话，如果你有个 diagraph，你怎么看 irreducibility？那个时候就不一样了，那个时候一定是 n by n 的才可以。我现在说的是 n by m 都可以。就是你找不到一个坐标变换，使得在那个新的坐标变换一下，可以写成分成不同的 block， 至少2个 block， 对吧？那如果它是 n by n 的时候，有更多东西你可以玩了。比如说你有个 diagraph， 然后你就想每个 entry 就是一个 node， 对吧？如果有 aij 这个 mij 这个 entry 是 non-zero 的话，你就有一个 connection， 对吧？那你怎么看这个东西是 irreducible 呢？就看这个 graph 是不是 strongly connected。那什么叫 strongly connected？ 那就换句话说 ，graph 任取2个 node， 2个点 ，you can always find the path go from one to the other one， 这就 strongly connected。这个是 special case， 必须得是 square matrix 才行。Okay, what we talk about, we say if a matrix, sorry, a system, dynamic system doesn't have to be a system. A system is monotonic. You already have a monotonic system. But if the corresponding Jacobi, of course, you have to be differentiable to be able to talk about Jacobi. If the Jacobi, the functional matrix, is irreducible, it's going to be strongly monotonic. So now back to the Rock-McDonald model we talked about in the beginning. So what's the Jacobi? Let's see what's the Jacobi in this case. So Jacobi. system 我们刚刚说了，这个 system 事实上是 strongly monotone。咱先看为什么它是 monotone。怎么 check monotonicity 呢？我们要看什么？它是不是合作，是不是 cooperative， 或者是看它的 Jacobi 的 off diagonal term。所以我现在 for simplicity 我 define 它叫 Jij。那我们来看一下，我最关心的是 off diagonal， 就是 J12 和 J21。只要什么？只要 x 和 y 不 touch 什么？不 touch 1，这个都是，首先它是大于等于0的，对吧？因为我们什么 x 和 y 都是 fractional variable, everything in between 0 and 1，这我们 already 知道了。所以说 off diagonal term 它是合作的，所以它是 monotonic。其实这一点说明它是 monotonic。第二点，这是 in 什么 ？in the biological region， 整个的 biological physical region 是什么？是刚才我们说的那个，是一个什么？是一个这样的 region。我们刚才刚刚是个什么样的 region？ 是一个 square region size 1 by 1的，因为 everything normalized by 1嘛，对吧？一个是 fraction mosquito is fraction human host， 所以这个时候 J12 和 J21 我们知道的更多，身上都是严格大于0的。但是 the point 是什么？这个它是不是 irreducible？ 这是不是 irreducible？ 是不是 irreducible？ 我们现在是一个 2 by 2 functional matrix， 但 fix x y 它是不是 irreducible？ 为什么？怎么看？我们可以想成什么？有2 node 嘛，对吧？你有没有办法从1达到2？有。有没有办法从2达到1？有。所以呢，对，它是 irreducible 的，对吧？这个时候必须得抛出 boundary， 就是
你得确保 x 不能等于1啊 ，y 不能等于 you got to make sure you ensure you're in the interior。所以这个时候我说的是 irreducible in the interior 这个，那这个就是告诉我们这个 system 这个 Ross McDonald model 它是 strongly monotone in the interior。这个清楚吗？这个很简单，这 monotonic system 这个可 powerful 了。可能就是我们在座的，一定是有老师是专家是这方面，可能我们在座的同学也见过这个东西，它怎么 powerful？ 说说看，看起来你是知道的。这个 monotonic dynamic system 它有什么好处吗？因为我们玩的是高维的 system， 甚至可能是 infinite dimensional system， 它有啥好处吗？我们为什么 care about monotonic dynamic 或者 monotonic system？ 你就说说你的直觉就好了。你想想，我们刚才定义 monotonic， 你们擦掉，还没，它也叫什么？你看它的第二个 name， 保序。对，它保序的是 order preserving 的，这就是很 nice 的。因为在高维的时候，两个 vector 怎么比嘛？怎么叫你比我大？对不对？所以它叫这不是个 partial order 嘛？对不对？它给你一种序，然后呢 monotonic system 它可以去 preserve 这种 partial order。那换句话说，一旦你有 system 是这样，很多东西可以做。首先，你不会想到这个 system 至少是低维的，它不会有 chaotic behavior， 它不会有那个 complicated 什么 strict attractors， 它的 dynamic， 因为你可以 preserve 它的那个 partial order 是相对来说是 simple 的。那当然，你做 analysis 的时候，它就会变得什么？就会变得容易了。你想想，你做 stability analysis 的时候，也许你就不一定再非得用 Lyapunov function method。然后我们再讲一个观念，我们就休息，好不好？再讲一个 notation。Yes。
In the definition of strongly monotone.
啊。
Results.
哦。
Strong-less, just less. X less than 1. The result.
Are you talking about here?
Yes.
这个是说，你如果 initially you have 这种 relationship, you are going to maintain.
Means that the result is strongly less or just less. Strongly less means every
Component, no, not strongly less. So here is our definition.
that's every result.
They're different, but right here, they're different by right here. This is the definition of the three. They are first of all x less than y under the partial order introduced by K is saying first of all y minus K has to be in the positive cone K. And second of all you need to guarantee, and Dr. Zheng talked about stronger version. So all you need to guarantee is they are not identical. That's all I'm saying. Okay? So it's not you're talking about, and Dr. Zheng talked about even stronger version. Okay. 要不我们 take a break 再来讲，我还有个 notation 叫 sublinear. Let's take a 15 minutes break, okay? I know many students come a long way from the other campus, okay? So let's take a 15-minute break. We're going to resume around 45-ish, okay? 10:45. Sorry. You already responded. The second one. Ross McDonald model 是这样子 strictly sublinear. In the interior of the biological physical region.
Sorry，插播一下，
哎，好，
那样子嘛，对吧？
可以呀。
那个导演可能要先讲一下，就是因为1月9号那个理论中心有那个叫什么？
有 event。
对，有一个活动，
对，
刚好是星期五。
对，
所以你1月5号的课，我们可能会 往前提1天或2天，那时候已经寒假了，应该就没有影响了。
1月5号是在这里，
我们就是想在这里啊，
不是那个活动在那
活动在
边，
那边，所以我们变成那一边的话，就将会那边就变成，因为星期5的那个活动是在台北，所以跟这个课是冲突啊。还是他们是说有个提案，就是把你们全部搬到台北，你们应该比较忙。
对，
把你们全部搬去台北上了。但是我是觉得，如果比较方便的话，就是可能提前1天或2天在这里，就是把那个课往前挪1天或2天在这里，这样子，你们 OK 吗？本来是星期5嘛
比如，说变成1月9号的话，变成2天，就1月7号礼拜3的中午，就是同一个时间可以吗？Shift 2 days，这个不是 delay 了，这是 shift early，可以吗？
你们比较喜欢星期3、星期4，你呢？
我看大家，我比较建议星期3啦，
那星期3可以吗？
大家行不行啊？就我看大家行不行？星期3可以啊
那我们。就暂
那我们
定提前2天，
好，谢谢。
到时候再 announce。
对，谢谢。
好，
所以后面
We're talking about
所以
we're
我先讲
schedule
期在台
之前我是写说后面要在台北嘛，那我现在打算要跟他们说，因为这边人比较多，所以希望都在这里。你们会抗议吗？如果你们让你们没有机会去台北，你们很生气，可以告诉我。OK，那我们就这样子哦。
So we reschedule the class. Sorry.
what what Dr. Wang is talking about. We're trying to reschedule the class, and on January 9th, I think is a Friday, and so we're going to move it reschedule to be Wednesday the same week, which will be January 7th. But you guys can double check your calendar to see if that is okay with you, and everything else is the same room, same time. Would that be okay? Yeah, that's what he's talking about. 好，
什么叫 sublinear？来，Let's see what's this. 一个 special case，这个 map 就是 vector field，就是vector field of our dynamic system，这是 general mapping。Is to be sublinear. For any length strictly between 0 and 1, for any axis. So this means component wise, you're in the first quadrant. That's all this is saying you're in the first quadrant. Yeah. 然后 sublinear 是说，如果你有一个 constant， 这是一个 scaling constant between 0 and 1。对，然后 you're going to have the following relationship. 那什么是 strongly 呢？不是 strongly，是 strictly。就是 inequality becomes strict。你再看一下我们的 model， 我们的 model 已经不见了。我们的那个 reduced version 那个2D 不是是 Ross McDonald model， 我也不记得了，看一下。
这个是我们 first component of the right hand side, second component。所以我们要 check 这个 inequality， 我们要对 component wise， 我们就看第一个 component 就好了。Clearly, lambda is common, so we can factor. Let me know if I copy anything wrong. Okay. And this looks right. So when we pull out those, all we know is right now is what? Everything is, 我们现在要是一步一步做 so everything is between 0 and 1. 所以这个地方我们知道什么呢？这个地方 lambda 是什么？ Lambda 是 the scaling factor between 0 and 1. So what we have? 因为 we're trying to connect this one to what? Lambda f. I'm trying to connect this one to lambda of what? F1 嘛，这就是 F1， 对不对？这个对不对？这都是不对，对吧？那同样的方法，你可以 check 第二个可能。就 x y between 0 and 1， 在我们的 biological phase中，那引地的是什么呢 ？In the interior， 这个时候 we have 什么 ？We also have this group。所以这告诉我们 by definition 就告诉我们什么？我们现在的这个 model 是什么？是 strictly sublinear in the interior of biological physical。我们要 introduce 这两个 notation 是我想给你们个 heads up。sublinear in the。刚才我们有个大结果对吧？是说什么？是说 stressful dynamic。说这个 R0 less or equal to 1 disease-free 是 global asymptotic stable in gamma。那第二个结果是 if R0 is bigger than 1 and endemic equilibrium is global asymptotic stable in the interior of gamma。因为是 2D 的，所以你会有更多的方法，因为维数比较简单，所以你可以 try the upload function， 你可以用 compare appendix， 这都可以去做那个我们留作 exercise， 那是用我们之前讲过的方法去做。今天为什么我们要 introduce 这个 monotone 还有这个 monotonicity 和这个 sublinearity， 就是因为如果有了这两个的话，事实上我们可以做出同样的结果，然后我们不需要引入什么 upload function 什么的，对，可以去这样做。然后这个我们会在我们讲下一章就是。Fundamental tools 讲完下一章，大概在结束的时候，我会说一个 example， 然后怎么去可能 come back revisit 这个，然后看怎么用这个东西去证明它。OK, all right. Let me clean this piece. Sublinear 的好处你们知道吗？如果有见过的同学 ，sublinear 有什么好处？就说高维的时候，我们怕什么？不能比嘛。monotone 给我们一种 partial order， 我们能比了，对吧？那 sublinear 是说，那如果你比如说这是 dynamic， 它的 vector field， 那它的 vector field 是它的这个 growth rate， 就是说它的这个 growth 是 under control 的，不会 become unbounded。还有什么呢？ 还有是说，比如说我们很喜欢的一个叫 comparison principle，你是可以 apply 的，对吧？你可以做中文是不是叫比较值原理，对不对？你可以去做，它有很多 benefits。就是说，你不但你刚才满足了你是这样的 model analysis system，你还有更好的一些性质，所以数学上 become more attractable。That's basically the idea, I think。好吧，你看看，看我们就是之前是想用5个 model 作为5个 motivating example 给大家授一下，就是我们数学上的基本的一些这个 fundamental technique。但是做这个的时候，我们引入了好多这个 terminology 呀，我们又引入了一些 fundamental result。所以下一个 chapter 我要给一个 quick review。Let's see how quick 。希望是 quick review。对，那当然，如果你感兴趣，刚才说的这个 topic，我可以写几个 reference。你们 OD 的书都看的是谁的？
是毕老师。
哦，OK，哦，对，这个许世碧老师的那个书，是这样写吗？
呀，
许世碧老师那书是叫 OD 吗？
呀
好
，with applications。
好 ，and application。
呀，
好，谢谢。对，这个是英文版、中文版。
英文的。
好，对，然后当然你你可以看。那你们的课上的是谁的呢？OD 的课上的是谁的？
也是
徐老师
大家都是徐老师是主要 reference，
啊，
是我们那个年代是靠定成的 reference，
对，
超
对，比较旧一点。
这个叫 theory of alternate equation，这很老了。对，这个可能 before many of you guys even born。对，然后你还可以看那个 Jack Hill， J.K. Hill， 这叫 OCD 嘛？2009年的那个，然后那个 monotone 那个 dynamical system 有一本很 classical 的那个 House Smith， 是 monotone dynamical system， 它底下还有一堆小名的，对 monotone dynamical system。好像是我还没记错的话，好像是这个，对，然后还有那个赵伟强老师那个，他看他第2版本，这个是 dynamical system in population biology。它有2个版本，大家可以看它最新的一版，第2版本是17年的。OK， 这样。我们现在做一个 I hope pretty quick。哎，这个这么跳也不好，我是在 review 这个，我们这样写好了，就是 basic or fundamental。Fundamentals tools。弃权。希望给一个 quick review， 因为我们这里不是每个同学都是数学 major。哎呀，我看怎么来呀？我们先第一个讲一些 notation terminology 吧。 So we consider open static in Rn。F 是，我现在假定很强啊，说它是这个是 continuous function，after the first derivative also continuous and the continuous first derivative。然后我们所有的 system 都是这个，在这一章里 dx 点 t 等于 f of x。我们叫它 system one。什么是说第一个问题 ？What do you mean by say a function is a solution？这是什么意思？这 solution 是什么意思？就是你带进去，它能什么？它解方程对吧？它得是 differentiable， 我再加一个字吧。differentiable。solution to 这个应该 on。这个意思吗？对吧？你带进去，它可以去验证，它就是它的解了。然后我们一个 notation 是说，如果你有 initial value problem， 当然，如果 f in C1 的，我可以 guarantee 它存在唯一的一个解。那个解我们叫什么呢？我们叫那个解是 xt epsilon， 就是 start with epsilon， 然后在 time t 的时候它是怎么变的？有的时候你可以看它会用 solution flow 做在 epsilon， 这是另外一个 notation， 就是 solution。所以我们知道 by fundamental theorem of differential equation 是让 ordinary differential equation， 那个你会存在唯一的一个解。我们这一章 about the very end we will talk about persistence theory，OK？ 但是我们会从头，我希望能有一个最快的从头到尾的一个 quick by fundamental theory of differential equations， 我们知道什么呢？因为 f in C1 这个事实上已经比较强了，我们需要的实际上 local ellipses 就够了。它如果 in C1 的话，对任何一个 x in where f is defined, the vector field dynamics is defined. There exists a unique. 太数学了哈，这个 notation 可以吗？数学没准。我已经在用了。Sorry, there exists unique 解。从0点开始的，我一定可以找到一个这样的区间，一个 delta， 它在这个0点的附近，这个解是存在唯一的。那现在的问题是说，有个问题，我们关键的解一般都是希望它全部存在的。那它的 maximal interval existence 是什么？我不写了啊，不写可以吗？就是说，如果就像这个定理告诉我们，至少 local 你会找得到嘛？那 idea 就是这样，这是0对吧？你至少在0的附近你可以做到。我现在知道解是在这里存在唯一。那 有没有办法可以一直延拓到全空间？有，就是说，当你考虑它的那个 solution flow， 它如果完全都落在这个地里，它不会跑出去的话，那每一点在这一点的附近，你就可以做同样的事情，对不对？然后在一点的附近，你又可以做同样的事情，你可以这样一直 extend， 然后 extend 到全空间。所以这个时候的 maximal interval existence 会 continuously extend。就全部的 all possibility， 对，如果你感兴趣的话，它是可以，只要保证它的那个 solution trajectory 不会跑出去就可以。那比如说，我们看一个 simple 的例子 ，dx dt 等于 x square，x 0那它的解是什么？我们大家都会解哈 ，we know how to solve this， 这个 super simple。那这个 maximal interval extents 是什么？在这个 toy example 里是什么？这个应该马上就知道吧，对吧？是什么呢？
拿到了。
对 ，clearly there is a trouble. You have to avoid the denominator to be 0. So on the integral line, first of all, you have to rule out this point, right? P equal to 1. So it ends up giving you two possible domains. Here is -infinity to 1, and the other one is 1 infinity. But 1 has to be the first one. He pointed out has to be the left one. Why is that? 对 because initial time， 我这一根只是我们数学的性质，不一定是0的，你可以 pick any time you like， 对吧 ？Where you start initially, that's your initial time。因为0在这里，所以它的 maximal interval extents 在这个透过example 就是它。啊 ，OK， 行。啊，现在我们可以定义。那什么时候一个 solution 是 equilibrium 呢？我们已经见过这个好多次了 ，in the last chapter。对，它一定是什么？它一定是 constant。然后呢？而且什么？是什么样的 constant？你的 system 全部都在这儿呢，对吧？对，它是 constant。equilibrium 就是说你 stationary dx dt 不等于0了，那所以一定满足什么？对，一定满足这个的，我叫 x bar 好了，因为它 constant， 好吧？对，那现在有了 equilibrium， 当然还有这个 equilibrium solution， 还有另外的好多 name， 就是你看文章的时候，你看书的时候会有叫什么？你说会叫什么？你说？对 ，steady state。那个时候更有趣的，比如说比如说 PDE 的时候，那 steady state 可不是 constant， 不一定啊，可不一定是 constant，it's not necessary to be constant， 对吧？它可能是什么？对 ，spatial dependent， 对，没错。Anyway， 它可能会叫什么 fixed point？ 当你看到 fixed point 就是这个东西 equilibrium solution， 也可能叫 critical point、station point， 然后也可能叫 steady state。就是说，当你看到这种station state， 可能指的都是它，指的全部都是它。它的名字最多，因为它研究的比较久。那如果有这个东西的时候，哦对，还有一个 periodic solution， 就这两个嘛。这个不是 PS， 不是我们那个对 photo PS，OK， 是 periodic solution for this class only. This is not the traditional name. 我们叫 XMPT。2也是 system one。如果什么呢？最简单的是 periodic of period what？ periodic solution to 这个 system of period something period omega t if this is true。你就想那个 predator prey 的那个 model， 它那个 predator prey 它们俩共同存在，然后会落入一个你生我长，你生我长，你生我长，就是你多了我少，你多我少，然后这样一个 periodic solution 的 case。那现在有了这两个东西，有了这两个东西，现在我们就要讨论，这是两个主要的 object， 我们就要讨论它的什么？我把这个地方擦了哈，我们就要讨论它的 stability。叫什么？自己啊，一个一个来 ，stability of equilibrium solution。但实际上我们都已经知道了，什么叫 stable 呢？或至少 locally stable 呢？就是说你 start， 如果你 close to 这个点，你就 stay close， 对吧？这是 intuition。那现在如果我们看它的 definition， equilibrium solution, let's call X bar, okay, give a name of this system one is said to be， 我们一个一个定义啊 ，locally stable。这个时候它还有一个名字，有时候你会看到那个书上或者是文章里会写 the upper of stable。是什么意思呢？我们怎么开 capture start close remain close？ 我们都数学的，我们说 for any epsilon bigger than 0, there exists a delta such that what? Such that if 你任何一个 solution start close， 我们写 neighborhood 好了。如果 initially x-link 它 in the neighborhood of x bar， 半径是 delta 的，然后 what's going to happen？ The xt 这 start close， 这是 remain close。这个尺寸是 how close you are 是 control by epsilon， 给定了一个 arbitrary epsilon， 你总能对应的找到一个 control for the initial condition start close and remain close， 这个是叫 locally stable。第二个是什么？是 locally asymptotic stable。那这是什么呢？首先它已经包括 locally stable 了，对吧 ？So the first， 那第二个是什么呢 ？asymptotic 是什么意思？
去除。
对，就是说，如果 initially sufficient close， 你对任何一个这个叫 x0 嘛，如果 initially sufficient close， asymptotically as time goes to infinity， 你要 approach 这叫 asymptotic， 这是 locally stability 加这个 convergence。那现在我就有问题了，我直观上想，如果我有一个一维的或者是二维的这个，如果其他的点都 converge to 我，那不就说明我已经是 stable， 事实上甚至有可能更强是 global 的 stable。就是我现在想问的是 convergence asymptotic convergence 能不能 guarantee stability？ 我的 question clear 了？我说的意思，这有一个点 asymptotically 我知道 trajectory 和 converge to 这个，我能 guarantee 它的 stability 吗？清楚吗？ 我说的是我有这个，我能 guarantee 它是 stable 吗？Why or why not？你怕什么呢？首先，我们来说这个可能是对的，是不对的，就说你认为是对的，是不对的。对，不对，肯定不对。为什么呢？如果你有一个例子，你马上就知道为什么它不对了。
跑出去然后再回来。
对，你比如说这个，我们之前见的这个，你记得这个吗？这是一个 homoclinic orbit， 它是 time go to infinity， 你是 convergent to p， 但是这个 p 它不是 stable， 它实际上是个 saddle， 它有3 branch 它是 stable， 3 branch 是 unstable 的。所以光有这个，我只是想强调，它不能 guarantee， 因为一会儿我们要讲那个 review Lassalle inverse principle， 我们只能 guarantee 这个。OK， 所以是 convergence does not imply anything about stability。好。然后从这个 asymptotic convergence， 我们也可以看出，所有的这些点这 in the neighborhood 都 attract to what？ attract to eventually converge to 这个，所以这些所有的这个点都落在它的 something 叫 Bayesian attraction 里。另外有一个观念叫什么叫 Bayesian attraction？ 这是 points， 这是 points。Bayesian attraction。那既然我们想知道 stability of equilibrium solution， 那我们先来看一下第一个方法，我们会用的什么？辅的方法，对吧？就是 linearization。我们 linearize 那个 system 去看它的 eigenvalue， 对吧？啊，所以说 without loss of generality， 我们 assume 这 fixed point 就是 origin。assume。如果不是的话，我们就 shift coordinate 就可以了。那我们当然知道了，那这个时候它 evaluate origin 就是0了，对吧？因为它是 fixed point。对，然后我们看，我们做 linearization 就是把 right hand side 的 vector field， 我们做一个 decouple。这些是什么呢？是 Jacobi evaluate zero， 这是我们看的线性系统，这是 higher order term。And you can check higher order term 有这样的性质。你 plug in equilibrium 它是0，然后它的 derivative 是0，所以它至少是它或 higher。那现在我想说的是说，我们来看它的 stability。那现在就是这样的，我们看它的 linearized system 是什么呢？不叫 y 好了，是 dy dt linearized system of 1 at equilibrium。那这个 system stability 是不是 super clear？ 这个 OD 一定学过吗？它的 eigenvalue 的 real part determine the stability， 对不对？它，对吧？所以说我们知道的是这样子的。 这是我们刚才之前讲上一个 chapter 反复用的。have negative real part。然后我们一定知道这一点是什么，我们的 equilibrium 一定是什么？不是 y 等于 linear system， 它一定是 locally asymptotically stable。这个不是充分的，因为有一个 terminology 我们要讲叫 something called hyperbolic。什么叫 hyperbolic？ 是如果你的 equilibrium 或者 fixed point 是 hyperbolic， 是 none of the real part can be degenerate， 或者是 none of the real part can be zero， 所以它是 hyperbolic。如果是 hyperbolic 的时候，这个才是 equivalent， 因为有零的时候，你要看 higher order term 它的 stability。那现在想说的是，这是 linear system。我知道y 等于0 for the linear system， 是 linear system。它现在只要这个 J 是它对应的这个谱，或者是它这个 fixed point 是 non-hyperbolic 没有退化的情形，它的线性部分的 stability 就可以决定整个原来 system 的 non-linear system 的 stability。所以我们就有它俩是 equivalent。换句话说，有的就是同样的，怎么写更换一下？我们原来这个 system locally asymptotic stable original system， 那这个是 original system 不一定 nonlinear。好，这观点我们清楚了，就是需要看它 eigenvalue。那我们上次讲了，我提了。看它的 eigenvalue 要看它 real part， 简单的时候我们可以去解，可是你不一定，我只需要知道它的 sign， 所以说我不想每次都去解，尤其是当你的这个 Jacobi 或者你的 system dimension high 的时候，你是不想一直去解的，所以这个时候你就要干什么？因为我只是关心它的 sign， 这就是上次我们提到的 something called Routh-Hurwitz criteria。The local stability。你 linearization 就相当于是 local， 我放了一个放大镜 zoom in， 然后我看它的 local behavior。如果 J 是 dominant， 这是为什么我怕它有 degenerate case， 所以要确保它是 non-hyperbolic fixed point 和 equilibrium， 然后 zoom in 看它的线性部分。我们知道是需要看这个，但是问题是我不想看这个。一个 uniform 的 way 或者 systematic way， 我们可以用这个 Routh-Hurwitz criteria。这是什么呢？我们做这之前，我们要定一个 something called Routh table。就是说 ，if we have a polynomial， 我们都已经写成 lambda 了。其实他就是想说的是，重点看的是它的 characteristic polynomial， 去决定它的 eigenvalue。所有的 AI， 现在假定它是 real 的。那它的 Routh table 是什么呢？The Routh table defines to be, let's say R RIG， 把它定出来。它是什么？第一行是 A0、A2、A4、A6。第二行是什么 ？A1、A3、A5、A7。然后这个是 R31，这事实上就是 R11、R21。totally 这是 n+1 by n+1， 这个是 0， 然后这个是 n+1 entry。那这里你就会想了，这个头两 the first two rows super clear. What's afterward, right? 我们写一下。从second row start from second row， 来看它是什么。还有个 recursive formula。This is the information coming from the previous row. You never need to remember this, but you got to know there is a recursive formula. And you just need to know where to find them. 那现在有个问题哦，如果比如说我举个例子来看，它的这个，我先说这个结果哈，结果是什么呢？事实上，我不知道有多少人做过 Hall bifurcation。Hall bifurcation 它的 degenerate case， 那个有一篇文章，它事实上是 degenerate Roos-Hurwitz criteria to capture degenerate Hall。Anyway，Roos-Hurwitz criteria 是什么？这个是看起来像代数的几个 all the zeros of the polynomial。have negative real part。费了这半天劲是为什么呢？是 if and only if each entry， 我现在要去写清楚是 n+1 entry in the first column。这个在台湾这叫第一行是吗？这个我很 confused。Anyway， 就是 all the entry in the first column of the root table。So in mainland China we call 列 is 摇行。Anyway, all the entry along the first column of the root table are non-zero. They have the same sign. You see, that makes the check super clear. 因为这个 polynomial 当 degree getting higher to touch, to find out the eigenvalue, you probably have to resolve like advanced mathematical technique or numerically. But this theorem telling us we can do everything. All we need to do is find out the root table. I know this is so tedious, but all of them is a recursive formula. And all you want to check， 我们看一个简单的 example 好吧？因为我这没这个 example， 是没这个 example。 我们现在想看 determine 它的 zero 的 location， 就看这个满足，看它的是不是 all the zero have not determined the location of all the zeros。你想，这是个 polynomial degree 3，事实上有 closed form representation， 它有 formula 的 cubic polynomial formula。一样，你可以做 fourths, fifths and whatever it depends on dimension of the system。那现在我们就看，我们用这个简单的 example 看它的 root table 是什么呢？你用这个 recursive formula， 你把它带进去，它的 root table turns out 可以看到 the first two rows。谁能告诉我 what's the first row？ 你看 ，so here A0 是什么？That's all we know, right? So what's the first row? First row is A0, A2, A4, and A6 with even index. 那你就带进去就好了。我有点抄错。2，sorry， 对不对吧？啊 ，so 没有了。这个是剩下的你 recursive formula 带一下。没有的 entry you leave blank of putting a zero， 因为我们这里有很多它是没有的 entry， 这是没有的 entry， 没有再继续计算的，因为所有的这个要套这个 recursive formula 的时候，它不一定所有的项都是有的。可是 all we care about 是什么？ All the entry in the first column. Clearly, all the entry in the first column, they're positive. Doesn't have to be positive. It could be negative. 只要你 have the same sign， 你就当了。所以说，你看这个 recipe 就 nice 了。我不管我的 system 是多少位的，10位、20位的 ，I can always do this， 对吧？去 check this。如果你要 analytic 去 check， 当那个为数，比如说。当 n 等于 2的时候，要求的是什么？要求的是什么？哎，我们可以再做个假定吗？我再做个假定。Sorry. The characteristic polynomial of the Jacobi value as fixed point, whatever that constant is， 叫 J。它是什么呢 ？Characteristic polynomial 是什么？是 determinant。对吧？是 determinant 它。所以说我把这个 character p of lambda， 我们一定可以写成是 lambda n。换句话说，我 normalize， 我 make sure the leading coefficient 是 1， 这个定理也是可以的，对吧？你就把 A0 非零，它是只要 degree 它就一定非零，你 normalize by 1， 你就可以做了。那现在来看这个 n 等于 2的时候，这是什么呢？我只要求 A1 和 A2 是大于都是大于0，这也是 equivalent to trace determinant plan， 因为 A1 是 negative trace，A2 是 determinant， 这是 equivalent to the trace determinant plan。因为什么 ？A1 是 negative trace，A2 是 determinant。我们要求 trace 是小于还是大于？这都大于 n 等于 3的时候，它是什么呢？我要求 all the coefficient one plus one more relationship， 因为我要 guarantee 这个是大于 A3， 所以说我们总是可以做的。这个就是 equivalent。当你是为数比较低的时候，你这个都是可以做得出来的。这是它非常 nice 的一个 component。我们就 don't have to worry about how big the eigenvalue。那当然 important 了，它的 real part how big 当然 important。可是这不是我们只关心它的符号的时候，这个就 good enough。所以是 very useful，very useful。So， 好 ，so let's talk about since we're studying stability of equilibrium, the other one is the function method. 那什么是 Biapon function method？ 首先我先定义一个 neighborhood。neighborhood contains zero。然后 consider 一个 function 叫 v，v 是一个 mapping from u 到 r 的，是一个 scalar function。那我们来看它的 Lyapunov derivative 是什么？你会看到这样的 notation， 或者是这样的 notation， 但是这个 dt 是 differentiate along 这个 system 的。我们现在是 system one solution system one， 那这是什么意思呢？我们知道 v 是 function x，x 是 function t， 所以 by 侵入这个是什么 ？Graded v dot dx dt， 这是 dv， 它是 v， 它是 x，dv dt。它的这个 method 就是这样的，就是说你要构造一个这样的 scalar function，so called Lyapunov function， 然后它要满足一些性质。最关键的一个性质是说，你想如果 solution 沿着这个 Lyapunov function move 的话，你想 guarantee 什么呢？如果你这一点是稳定的，你想 guarantee 什么呢？你希望这个 Lyapunov function 它会什么？随着你的 solution move， 希望它会对不增，至少不增，才能保证这至少是 locally 的，是 stable 的 ，exactly。那换句话说是要这个东西是小于等于0的嘛，对吧？这是我们要求的，是相当于是 Lyapunov function 它的 gradient， 这是个 scalar function， 它的 gradient dot product with the vector flow， 你要是小于等于0是什么意思呢？你最多是什么？是 perpendicular to each other。那换句话是说，它的 level curve of Lyapunov function 和你的这个 vector field， 因为它 gradient 的方向和那个 vector field 的 perpendicular 是说你的 level curve 它是 tangent to the， 它的 gradient 方向是这个 level curve 长得最快的方向，对吧？是它变得最快的那个方向。那如果我还有个颜色，如果它和 f 是什么？是你的 vector field， 你的 directional field， 它是 perpendicular， 就是等于0的 case， 对吧？那这是说明什么？你的 level curve 和 Lyapunov function 是 tangent to the 什么 ？to the vector field。啊，还有一种就是另外一种情形。这是严格小于0的时候， 所以这个时候你看它是 pointing inward， 就是这个意思。说你的 solution flow 或者你的 vector field either tangent to 这个对不对？或者是 pointing into， 这是 compared to level surface of diagonal function。那现在它的这个 diagonal function 的 method， 我们现在 finally 可以说它是什么了？所有的 setup 是 the same 的，都是这样的 setup。你给一个 neighborhood contain 啊，我都忘说了 ，sorry，x bar equal to 0 is a equilibrium solution， 这是 without loss of generality。如果不对的话，你就 shift 你的 quantity 就对了。哎
gradient 相关，
那相关，对，
内相关，
是因为 level curve 它要慢慢增长嘛，所以应该是要变大，所以
那个看往外相关，对的，是它长得最快的方向，对的，没错 ，good point。对，是它增长的 greatest descent。对，哎，这个不对，这是拉普朗斯了，sorry， 我再换一个啊。然后这个 F， 这是 staircase。
向内。
Point either tangent or point inward， 因为要到 product 小于0，对，没错，这个 idea 清楚吗 ？Is the idea clear？ 你看 geometric 很清楚，我需要，这是我的 diagonal function 它的 level surface， 沿着它 move 的时候，你的 solution flow 最多只能 tangential， 或者是要什么 strictly point inward， 这样才行。对，那到 product 小于0是要钝角吧？
钝角，
对吗？我刚才画了个锐角，是不是？对，好，谢谢。我 back to this， 非常好。我们需要几个条件。你要是量衡方式，你得有几个条件。第一，在所有的你考虑的这个范围内，所有你考虑的范围，它都是非负的。这个正负不是 necessary 的。我只是说假定，看第二个啊，它的最低点，我只是假定它的最低点是在0点达到，但是这个0全部是相对的，我可以说我 minimal level 是 -100， 那这个时候你就是 Vx 大于等于负的100，然后这个是等于负100，是 x 等于你的 fixed point。明白吗？这是 mathematical simplification。第三个是最重要的，就是我们刚才画了一堆的那个，它的 diagonal derivative 或者 v dot 就好了，它要小于等于0。那这个时候我们可以 guarantee 什么？我们可以 guarantee 这个 fixed point。这个 fixed point 是什么？是 locally stable 的，我不应该写 locally， 我是写 stable 的。告诉你为什么不一定是 locally 的。第二个结果 second result， we make the same assumption 1, 2, but we change 3 to be strictly less than 0。这个时候 the fixed point is going to be asymptotically stable， 就说你不能 stuck there， 你还要 keep going， 因为你的 Lyapunov function 它要一直 decay， 直到你能停到那一点为止，所以它有 asymptotic， 它有 convergence。为什么我没有写 local？ 因为这个 neighborhood 可大可小，比如说我取全空间的时候。这个 stability， 刚才所以 talk about stability 或者 asymptotic stability， 它都是 global 的，取决于你取的空间。所以这个里头我们没有写 local 或者是 是 global 啊。最后一个，如果你 unstable，你也同样可以用 diagonal function 去刻画。unstable 怎么办？我们现在说的 stable， 这是 stable 的，这是 asymptotic stable。那如果 unstable 呢？对，你说能量不递减了，对不对？你刚刚说是不是能量不递减了？
那个 V 是第一个要大于零，第一个
要大于等于零。
如果
哎
你允许它很多等于的话，那你可能有，就代表你允许它很 equilibrium 在附近。
这个第二个条件是说，
第一个
对，第一个条件它是非负的，说能量至少是，就是说它现在假定 the minimal diagonal function or functional， 它的 minimal value 是 zero， 这只是数学上的一个假定，零只是它一个假定。
担心如果你允许，
你说太多零啊，
对，
不能啊。第二点 guarantee 你不能啊。第二点 guarantee，
if and only if。
第二点
第二个已经排除掉
第二个 guarantee， 如果你是零，你只能是在这个 fixed point，you cannot have more than one。
对。
我们对这个我又忘说了，这个是necessary sufficient 一般的。
我没有看到二。
哦，
对
对，你说的对，就是第一点它要非负。这是哎说，
对不起，然后第二个、第三个
对
是要扣掉零，因为那个 B
对，
可能
我这个就是自己写的，没有，对
第一个不用，
第二才
第
要，
一个不用扣，
第一个
第一个等于
第一个定理
对的是在零，
这个要扣
对对对，，这个要扣的。
这个是这是对的，因为那一点是零啊，它是领导的，没错。到那点 stuck， 这是为什么我们能做 Lassala invariant principle， 就是说在 where the largest set such that v dot equals to 0就是 single point， 就是这样。对，谢谢。还是得看讲义哈，不看讲义这个有一些数学上的对。Anyway， 那现在第三个问题，我们最后一个讲完我们就不讲了。unstable 怎么办？我现在是给了一个充分的，这不是充要的了。我还是考虑零点的。我说在这一点它还是零。然后第二个是说我可以找到一个 direction， 沿着这个 direction 发生什么了呢？它不是最小，它不是最小，沿着这个 direction。v dot 就可以了 ，v dot 是小于等于零的。这时候我们只要找到一个 direction， 那我们就知道它是 unstable。换句话说，你比如说你想 saddle 有一个方向它是下，它是 attracting， 另一个 saddle 大家知道哈，就是比如说二维的，我有一个方向它是 attracting， 一个方向它是 repelling 的。那沿着那个 attracting 它是往下走的，对吧？但是沿着另外一个 direction， 你就想沿着另外一个 direction 它是往上增的，所以它可以继续往下降，它就离开了这个 saddle fixed point。
那个 V 第二个条件，那个 V 小于零，那个
没有是小，就是说我 pass 这个 direction， 我可以 further decay， 它不是最小了，
这是 V dot，
不是 v dot， 是 v， 它的 value 可以 further
你
decay。
的 value 是所以
Further
这个
decay
V 你就不需要
对啊
增定的。
对，不是你要证明它是 stable， 你需要这样，对不对？你不证明它不 stable， 我只要找到一个 direction 它不对就行了。这个不是 necessary 的，是 sufficient。我是想说的是，我们 capture stability 有很多方法，比如说刚才我们讲的是什么？刚才讲的是 spectral analysis， 通过 linearization 看它的 eigenvalue， 只要有一个 eigenvalue have positive real part you're done， 对吧？有一个 direction 你就是 repelling， 这是一种方法。当然你也可以做这个，对。好，今天有点长，抱歉。That's all for today. So I'll only save you guys a few more minutes. So that's all for today. We're going to continue the discussion next time. Let me know if you have any questions, comments, concerns at the end. 但是一定要把那点扣掉的，不扣掉导数在那一点就是0点，对，就相当于你想这个例子就对了，它一定会 end up 这儿，但是它 end 级到这一点，它一定是离到就是0。
谢谢。
非常感谢各位老师和同学。对